Let's suppose that we are in a chatbot setting. Here's our little robot, and the robot asks, "Hey, what would you like to do?" And then let's say that you as a user, you reply by saying, "Play ping pong." To put it in chatbot terms, the user just did two things. The user made it clear what the intent was. The intent here is to play a game. If the chatbot is clever, not only is it able to detect the intent, but it's also able to detect an entity. If you want to have a good dialogue system, it is important that your chatbot not only detect what the user wants to do in the intent, but that it's also able to detect these entities alongside of it. At Rasa, we are very interested in designing systems that can do this very well. So we're happy to announce a new architecture, DIET. DIET stands for Dual Intent and Entity Transformer. It's a neural network architecture that we've designed to handle both intents and entity extraction. There's a lot of properties that we think are very interesting about this approach, and we've also open sourced it inside of Rasa in our latest release. The goal of this series of videos is to do three things though. First, I would like to explain how DIET works. Second, I would like to explain why DIET works. And finally, I would like to demonstrate this in a benchmark. So we will show you how you can use this new technology in your dialogue systems. This will be split up in 3 separate videos, and in this video we will start with this, explaining how DIET works. So what I will do now is I will explain the separate parts of the architecture. What I'll assume is that we had a user, and that this user had said in the past that the user wants to play ping pong. Now this is a record from our training data. So we know that this was an entity. We know that there wasn't an entity here. And we know that the original intent was to play a game. During training, this information is fed to the algorithm. The intent, for example, comes in there. The entities are dropped in here. And these tokens, they are inserted here. There's one small exception though. Sometimes we mask these tokens. The algorithm that we have here doesn't just learn how to predict intents and entities. The algorithm also preoccupies itself with predicting tokens in an utterance. We'll come back later on why this is useful. But just as a starting point, we see all the items going into the algorithm. Let's now look at the separate parts of the algorithm and see how they are connected. I will first discuss everything that's happening on this part, the bottom end. And in particular, let's start over here. I have the token play. And this token play will be handled by 2 separate paths. The bottom path is the pre-trained path. That will be this part. And this pre-trained path accepts a pre-trained neural network. That can be BERT, that can be GLOVE, or CONVERT. And what all of these algorithms do is they accept a token and then they output a numeric vector. The design that we have here is that you can plug and play your favorite pre-trained network for this task. And this pre-trained network is used not just here, but also here, and here, and here. But we also have another path, this one. This path is slightly different. What happens here is we generate sparse features from this play token. So you can imagine that we have some sparse features that can be regarded as the one-hot encoding of the word, but we also take character n-grams. So we have the character n-gram of 1, that is to say take all the letters. So in this particular sparse encoding, we would have 4 letters for the word play, because P, L, A, Y are 4 separate letters, and the rest would be all zeros. But we don't just have one-hot encoded characters, we also take the n-grams. We take the 2 gram, 3 gram, all the way up to 5. But these are all sparse vectors. Next what happens is this is passed into a feed-forward layer. So first you can imagine we concatenate everything. We have a long vector with ones and zeros, mostly zeros because it's sparse. And then this is connected feed forward style. And you could say that it's something like taking an activation function, taking this array X, multiplying that by a matrix W, and adding a bias term. That's what's happening here. Afterwards, we concatenate these two things together once more. So we have our orange numbers and our blue numbers. But this purple array is what comes out here. And that's being inserted in another feed-forward layer. The array that comes out over here would be over here. And the base settings that we have is that what comes out here is a 256 floating point array of numbers. It's a vector. But there is an interesting characteristic that I would like to mention about the feed-forward layers that we have here. And this property is copied across all of these feed-forward layers. Typically in a dense layer, you would have lots of nodes on this end, and lots of nodes on this end, and you would have a connection from one node to every single other node on the other side. And here I'm just drawing a few, but you can see that actually we are drawing lots and lots of weights, all of which have to be learned. If you want to keep your models lightweight, one thing that you can do afterwards is you can prune the network. You can say, let's maybe remove this arc or set this connection to 0. But this can be a long and arduous process. So instead, all the feed-forward layers that we provide, they are sparse from the get-go. The layers will offer dropout, but more importantly, we drop 80% of all the connections to start with. The feed-forward layers are more lightweight this way, which is beneficial for the chatbot setting. In any case, what's important is that what comes out of one of these token blocks is a vector, and that is being passed onto this layer. And that is happening here, but it's also happening here, and it's also happening here. We should now discuss, though, what these special tokens seem to be that go into our architecture. Because this is a token, this is a token, this is a mask, and this is a special class token that we should discuss. I will start by focusing on this class token. The idea of this class token is that it's something that will summarize the entire utterance. So again, if we were to say play ping pong, then there's probably something that we can do that summarizes this entire sentence instead of just these separate tokens. And the way we do that slightly depends on what type of pre-trained word embedding we are using. So I'll make a similar diagram. In the pre-trained path, what comes out? Well, that depends on what pre-trained model we are using. In the case of glove, then we just take the mean of all the word embeddings that happened before. So there will be the embedding that came out of here, the embedding that came out of here. All of these known word embeddings, they are summarized here. That's in the case of glove. And in the case of Barrett, and also in the case of convert, we just output the sentence embedding here. Either way, we still get a numeric vector coming out of here, just like here and here, but the difference is that this embedding is the summary of the entire utterance. For the sparse features, a similar thing happens. We will take all of the sparse features for the separate tokens, and we will just put them in here, just as a sum. So those are all the separate one-hot encoded sparse variables. And then after that, it will go through a feed-forward layer. And again, that's a sparse feed-forward layer. And then these results will be concatenated, and they will go again into a feed-forward layer. And again, the output here is again an array, and again of the same size as what we had before. Now, a thing to note, these feed-forward layers, and also the one over here, they share weights. So the formula that I would have here and the formula that I would have here, this weight for this feed-forward layer is exactly the same as here, and here, and here. Just like with this one. Same here, same here, same here, same here. So one way of looking at it, what we are putting in here are features that come from these tokens, while what is going in here is a feature that summarizes the entire sentence or utterance that we pass it in. Now, I've explained this class thing, but let's now zoom in on this mask, what that exactly means. The end goal of our model is to make sure that we can classify intents as well as entities quite well. But in an attempt to also have the model be a general language model, which is kind of a regularization tactic, another thing we've added is this notion of masking away words. So during training, what we do is randomly we remove some words, and this will become a mask, so to say. And it will be the goal of the algorithm to predict what word was uttered here. The mask is being input here as an example. During a training procedure, we flip a coin, and that coin flip says whether or not a variable is masked. Then, if a token is masked, then we do know what the token actually was. In this particular case, I am pretending that I am masking the token Pong here. Now, this mask that you see here is a TensorFlow mask object. It's not a token in any way or form, and it is meant to indicate that there is something missing that requires prediction. Because there's a mask set here, there is no block here. And what you will also notice is because the mask is set on this token, that there is now also an arc going through this transformer layer, which I will discuss in a moment. But it's going through this transformer layer and ending up over here. Conveniently, close to where this Pong token is. Notice that the Pong token that we have here is going through a similar block as the other tokens. Before the mask and the embedding that it's causing meets up with the Pong token embedding, they are first going through an embedding layer, which is a TensorFlow embedding layer, which in essence is just a feed-forward layer. But the idea here is that this transformer that we have here and this embedding layer that we have here, can they perhaps predict what word is supposed to go there? And if it can, well, then we can say there's a certain loss for the mask. A few things to briefly point out once more. These feed-forward layers, they are all shared. Another thing to remember is that these feed-forward layers, they are somewhat sparse. They are not fully connected. We drop about 80% of all the weights. But what I do hope is clear is that here we have a mask. It's going through an architecture to come to a representation. That representation has to be something that our algorithm learns. And then Pong is being passed through a token block. And this will give us an indication of how well our model is able to generalize the language. This is only part of the total loss that we trained for, though, and I will come back to that later. But I hope it's mainly clear for now how this mask relates to this Pong over here. We have to learn the entire representation along this path, and because they come together, we get ourselves a loss that we can train on. And I would just like to briefly note that something very similar is happening between these two. Just like this mask in the end was related because the mask was the missing value and Pong was the actual label that we're trying to fit on, we could say that this class token is a summarization of the entire sentence, and that is something that should predict the intent. So notice, in general, a very similar path. This class token is also moving through the network, through an embedding layer, which again is like a dense layer. But then here it meets up with a representation of the actual intent that we're trying to fit on. So also here we have our input and our output match, and we can check for a similarity. Before we had a loss for the mask and the missing token, but now here we also seem to have a loss for the sentence representation and the user intent. The only thing that's missing right now is this entity loss that we have here. And to explain that, I'm gonna have to mention this transformer. So let's zoom in on what is happening here in this transformer layer. What goes in, what goes out. So we have this block. And in the example we currently have, there are 4 things going in. There is the vector that came out of the play token block. We have a very similar thing happening for the ping token. We have our mask here, and we've got the vector that belongs to the class token. Now what we see is that there are also outputs on top of this block. So looking at this, you might be reminded of a recurrent neural network. Those are the kinds of neural networks that have recurrent connections. The idea behind a recurrent neural network is that you can learn more about the relationships between words because information is being passed along not just in a feed-forward fashion, but also in a more recurrent fashion. There are many variants of this, like the GRU and the LSTM, but it should be said that we are not using a recurrent neural network architecture here. Instead, the architecture that we use here is known as a transformer. And a transformer block doesn't use these recurrent connections. Instead, what is in the inside of here is an attention mechanism. The attention mechanism is one of the main features of the transformer block. And the details of this will be explained in another video. Transformers really deserve a video of their own. But one thing to keep in mind that's important is a transformer block is an architecture where recurrent connections are substituted with an attention mechanism. And another thing that is important is things are going in here, and the equal number of things are going out here. Now, what comes out on this side can branch off. And what's going out here is a large numeric vector, just like before. And we've seen examples of such a branch divide. We can see that one happening here. But one other nice property of these transformer blocks is they kind of work like Legos in a way. So if I zoom out and take a look at a transformer block, there will be things going in on the bottom and an equal number of things going out on top. And that means that I can put another transformer block right on top of it. And that is also what we do. The base settings that we provide will have 2 layers of transformers. Note a few small things. We have 2 layers of transformer blocks here, and the class token that goes in comes out over here, and that class token is picked up and combined with the intent that we have in order to eventually come up with a loss for the intent. The tokens that are masked will then also be picked up. The example we had here was for Pong, and that will eventually be combined with the token that we've masked, and then we have the mask loss. All of these other connections will go into one final layer where they are combined with the actual entities before being combined into an entity loss. This layer is the conditional random field layer, and once we discuss that, then we'll have come full circle in how we get to all these losses. CRF stands for conditional random field, and the implementation that we are using is from the TensorFlow 2 add-ons package. The goal of this final block is to classify which tokens belong to certain entities. So in the example that we had play, ping, pong. So here we had play that didn't belong to an entity, so I'll just put O there. For ping, we had that's a game name, and the same for pong. Now below here, we have the outputs of the transformer block, and these are all numeric vectors. Notice that the first embedding came out of the transformers and the token blocks for the token play. Here we had the same thing for ping, and note that we had a mask here. Even when we replace a token with a mask, then we still know that there was an entity over there, one that we would like to be able to detect. In the CRF block,
all of these things will now be combined. Inside of a CRF block, what you will find is a small feed-forward layer that accepts the input from below and then outputs a classification, namely, which entity do I have here? But it also features one extra thing. In between these predictions sits a transition matrix of sorts. And both these feed-forward layers, as well as this transition, are things that are trained. These things have to be learned during training. And the idea behind this transition is that perhaps if there is a token that is an entity over here, then that might do something with our belief that there is one over here and over here. And that's what these transitions will try to capture. In the end, we have our predictions, which means that we can combine that with the actual entities that were there. And as such, we might be able to say, hey, this is predicted correctly, and so is this, but maybe we made a huge mistake over here. What we can then do is we can take all those losses, right? So we have our loss, and that is something that we can try to optimize. And those losses, that's what you see over here. So that means that we are now sort of getting full circle. We have a loss for entity, we have our loss for the intent, and we have our loss for the masking. And what we do is we just add all of these three losses together, and it's that loss, and I cannot draw enough arrows towards it, but it's this total loss that we optimize for. And when we do that, we have an algorithm that is trained to do multiple things. Let's now take a step back to see the big picture again, and wrap up for this video. This is the overview of the entire architecture. When you zoom out, you might realize that this transformer block that we've got right here, that is a central piece. Because let's look at all the things that come out. We have these features that are combined in the conditional random field. And when you combine it with the entities, you will get to your entity loss. Also, another thing that comes out is this representation for the class token. And when that is combined with the intent, then we get another thing we're interested in, which is this intent loss. And finally, if we have tokens that have been masked, we can take the representation that comes out of the transformer as well, and then combine that with the representation of the token that is missing. And this in turn will give us our masking loss. And when you've got an algorithm that tries to average these losses together and come up with something that can do all three of these tasks, well, then we like to think that we have an algorithm that can be very useful in a chatbot setting. In this video, we've discussed all these separate parts and how they work. We've discussed how we get to the final loss, and we've also discussed how these token blocks work, and we've reviewed some of the other mechanisms in here. We will make a separate series of videos for this transformer because it's quite important, but in the next video for Diet, we would like to talk about some of the design decisions that we made in designing this architecture. I hope you'll stay tuned for that.